Hello everyone. In the previous video, we introduced quantum gates and circuits as a means of performing computations on qubits. In this video, we will present our first quantum algorithm, Deutsch's algorithm, to demonstrate an example of quantum circuits and quantum advantage in action. One of the advantages of quantum computing over classical computing is a feature known as quantum parallelism. The idea here is that we can efficiently create a superposition over all n-qubit quantum states and compute a function on all terms with a single computation. Assuming an initial state where all qubits are set to 0, to create a uniform superposition over all n-qubit computational basis states, all we need to do is just apply a Hadamard operation to all the qubits, as each Hadamard gate maps the 0 state to an equal superposition over 0 and 1. As we explained in the previous video, we can compute any classical circuit F using some sequence of gate operations noted as UF, which maps x and y to x and y, x or f of x. This means that if we have a uniform superposition of all n-qubit inputs, and we want to compute a function f from, let's say, n-bit strings to m-bit strings, and an additional m qubits in state 0, we can simply apply UF to then get the superposition where the first n qubits correspond to an input x and the last m qubits correspond to the given value of f of x. Now, of course, as we explained in the first video, this technique does not give us an immediate advantage to solving any problem that requires testing an exponential number of inputs, as the process of reading the result to solve the problem we want is non-trivial. However, as we will see in Deutsch's algorithm and its n-qubit generalization, the Deutsch-Josza Algorithm, there are problems for which we can utilize quantum parallelism to get a strictly quantum advantage. You know, I've talked about quantum advantage a few times now, but you may be wondering how we actually quantify this advantage. Well, we define the runtime of a classical algorithm by the asymptotic scaling of the number of operations required as a function of the size of the input. For more information about runtime analysis in general or classical algorithms, consider checking out my series on algorithms. In the context of classical circuits, we usually have two measures of complexity: size, meaning the total number of logic gates, and depth, referring to the number of parallel layers of computation. These concepts can be defined equivalently for quantum circuits in terms of quantum gates. Let's now move to discuss Deutsch's algorithm. The setting for this problem is simple. Suppose we are given a function f from one bit to another as a classical circuit. We are promised that this function is either constant, meaning that f of 0 equals f of 1, or the function is balanced, meaning that f of 0 is not equal to f of 1. We are then given a decision problem where we must determine whether f is a balanced function or not. If we consider this problem in the classical setting, then it should be easy to see that we always need two evaluations of f to solve this, as we need to evaluate both f of 0 and f of 1 separately. However, in the quantum setting, it turns out that we can actually do better. In particular, we can solve this problem using the following quantum circuit, which only utilizes one evaluation of f. As you can see, the first two steps simply correspond to the quantum parallelism setup I described previously, with n and m being both equal to 1, with the only slight difference being that I have initialized the second qubit to be 1 rather than 0, and we are also operating on this qubit as well before applying UF. Let's look at the state of the system after each stage of operation. Initially, we of course have the state 0, 1. If we now apply h to both qubits, we get plus minus. Looking at the state after applying the classical circuit, let's think about what happens to the state. In particular, if we provide input x, then the 0 and 1 in the minus state will get XORed by f of x. If f of x equals 0, nothing changes. But if f of x equals 1, the whole state gets negated, meaning that we can represent the action of this step on x minus as -1 to the f of x, x minus. Consequently, we have that the state psi 2 can be written as follows, depending on whether f is constant or balanced. When we apply the final Hadamard transform, we simply map the first qubit to 0 if f of 0 equals f of 1, and 1 if f of 0 does not equal f of 1. In other words, the first qubit is simply in the state of f of 0 XOR f of 1. Consequently, if we now measure this qubit, 0 tells us that the function is constant, and 1 tells us that the function is balanced. Now, obviously proving advantage for a single qubit is pretty lackluster. But as it turns out, we can actually generalize this advantage for the n-qubit version of this decision problem, where we instead have that a constant function is defined to be one that maps every input to the same output, which can be either 0 or 1, and a balanced function is defined to be one that maps exactly half of the inputs to 0 and the other half to 1. It turns out that we can simply use the same exact circuit that we used for Deutsch's algorithm, but instead we just replace the single H gates with n H operators acting on all the qubits. Let's map out how the state changes at each step. We have this initial state. For psi 1, we get n plus states and a single minus state. These n plus states effectively just consist of a uniform superposition over all n-qubit computational basis states. Using that mapping we defined previously for UF, we have the following for psi 2. For psi 3, we need to consider the general form of the HO times n operator, whose action we can write as follows. Here, x.z represents the bitwise inner product of x and z modulo 2. In other words, treat bit strings x and z as 0, 1 vectors, take their dot product, and then mod the result by 2. Using this, we can then evaluate psi 3 as follows. Just as before, we now want to measure the first n qubits to determine whether f is constant or balanced. Let's look at the term corresponding to z equals 0. Here, we have that the inner product vanishes, meaning that we simply have this expression. If f is constant, we have that the phase factor is the same for all x's, meaning that the sum over all 2 to the n choices of x adds constructively, giving us the following. Since this state has norm 1, this must mean that all the other states vanish. In other words, we will always measure z equals 0 in this instance. However, if f is balanced, we have that half of the x's correspond to a phase of +1 and the other half to a phase of -1. Consequently, when we add all these terms, they will interfere destructively and all cancel out, giving us 0. Hence, this means that 0 cannot be measured in this case. Hence, we have that if z equals 0, then f is constant, otherwise it must be balanced. Let's do a complexity analysis on this problem for the n-qubit case. Classically, in order to test whether f is constant or balanced, we have to be able to distinguish between the two cases. Since we have no information about the distribution of outputs, all we can really do is really just randomly pick inputs and check their outputs. If we ever get outputs 0 and 1 for different inputs, then we know that the function has to be balanced. Since a balanced function has 2 to the n-1 0 outputs and 2 to the n-1 1 outputs, this means that in the worst case, we need to perform 2 to the n-1 plus 1 evaluations of f in order to solve this problem, giving us an exponential time complexity. In the quantum regime, however, we only require a single application of u of f in order to solve this problem, presenting a significant speedup over the classical alternative. Altogether, we discussed our first quantum algorithms, Deutsch's algorithm and the Deutsch-Josza algorithm, both of which present an exponential speedup over classical algorithms for their respective problems. This concludes our general introduction into quantum computing. In the next video, we will look into the quantum mechanics of open systems by introducing density matrix formalism. I hope you enjoyed this video, and I will see you next time.